Okay, so we're now starting chapter 10. That's a review of classical field theory. And what I want to start off by doing is explaining to you the structure of classical field theory. Classical field theory is a very natural generalization of the description of many particles in mechanics. And that means that if you can do classical mechanics, you can do classical field theory. So that's the point of view that I want to promote and explain. So, okay, so let's start. Let's imagine that we start off with a description of one particle. Okay? So we've got one particle. Now, if we have a single particle, what would we want to describe? Well, the position of that particle. Let's call it QFT. If we generalize this to n particles, then what we will want to describe is Q, and now there's a superscript A of T, and A goes from 1 up to n. Changing the particular value of A that I'm considering means changing the particular particle that I'm considering. And when I come to thinking about field theory, well, now I think about a field, phi, which is a function of space and time. That's what I mean when I talk about a field. And what I'm going to invite you to think of that, I want you to think of X as the natural generalization of A. So A was a discrete index, and we have now generalized that to be continuous. You can always generalize discrete indices to be continuous, and that's the generalization in going from n particles in classical mechanics to field theory. We've generalized A to give you X. So I want to explain some of the other possible ways that you might think about it, which are wrong, and I'm going to explain why they're wrong. So the first thing that you might think, and this is often what's said, you're told that to do relativity, you generalize T and you replace it by T and X, okay? Now, that's incorrect. So let me try to explain to you why I would say this is incorrect. If you're solving a problem in mechanics, then the initial conditions that you would specify, you'd specify the position of the particle at time 0, and you would specify the velocity of the particle at time 0. And now that would be that would lead to a unique solution in mechanics. If you are doing field theory, well, if I think that I replace T by T and X, I might think that I should specify the value of the field at T is 0 and X is 0, that I can specify. I might also specify the time derivative of the field at T is 0 and X is equal to 0. I might also specify the X derivative of the field, again, at the initial time and at the spatial origin. The Y derivative of the field, again, at T is 0 in the spatial origin. And finally, the Z derivative of the field, and again, at the initial time and at the origin. It's completely ridiculous to think that we've solved, we've determined the initial value problem. I mean, the field has an infinite number of degrees of freedom in it, and in total, we have specified 1, 2, 3, 4, 5 numbers. So just 5 numbers. This is not enough initial conditions. We would have to specify the field and its time derivative at T is equal to 0 to get a unique solution, and we'll be seeing that. So really, thinking that T is replaced by T and X is quite silly, and it's led us to a silly guess for what the initial conditions are. Let's instead use the correct link that we're meant to have. So the correct link is that we're meant to specify, generalize A into X. When we think in that way, well, what is the initial condition for a set of n particles? Well, we need to specify the initial position of every particle, and we need to specify the initial velocity of every particle. So now I would have to specify two n numbers to specify the initial value problem, to give the initial conditions for the initial value problem. For the field, I would need to specify the value of the field at time is 0 and at all positions x, and I would need to specify the time derivative of the field at time is 0 and at all positions x. Well, this is an infinitely bigger amount of initial conditions that I've specified. And notice something, when I'm talking about degrees of freedom of my system, if I say, well, 1 degree of freedom is the degrees of freedom for one particle, so maybe a degree of freedom is the pair, the initial time and the initial position, then A labels degrees of freedom. And for an n particle system, I might think I've got n degrees of freedom. You could also say 2n because it's 2n numbers that we have to specify. But A is really labeling distinct degrees of freedom. From that way of thinking, X labels distinct degrees of freedom, and we see that we're dealing with a system that has an infinite number of degrees of freedom. And that really is how we should think about field theory. So we are always going to think about field theory as a generalization. We've generalized the discrete index A, telling us which particle we're thinking about in a collection of n particles, to a continuous index x. Okay, now let's use this way of thinking to work out a few more quantities. Good. So when we studied a single particle, well, how did we specify the dynamics? Well, we spoke about a Lagrangian. And this was given by the kinetic energy, which was a half mq dot squared plus the potential energy. When we come to describing n particles, well, we will have a Lagrangian for each particle. Each particle will have a kinetic energy. So I'll have a term like this for each particle, and each particle will have a potential energy. Okay? And then to get the total Lagrangian, I would sum from A is equal to 1 to n of each of these Lagrangians. And the Lagrangian, of course, is a function of t. So that's what the Lagrangian would look like for the n particle system. Now, looking at this last equation in particular, well, I know how to generalize this. If the index A becomes continuous, I would say my Lagrangian equals, and then instead of a sum over the discrete index A, I would have an integral over our continuous variables inside x. So this would be an integral d3x. I would need to integrate a new function. Because L is indexed by A, this new function will depend on x, and it will depend on t because LA depends on t. So that's the natural generalization of the equation in the blue box. L is often called the Lagrangian. Well, it's not often called the Lagrangian. It is called the Lagrangian. And curly L here is called the Lagrangian density. Now, in field theory, the thing that we focus on, the thing that is important, is the Lagrangian density. So the next thing that I want to explain is, why do we focus on the Lagrangian density and not the Lagrangian?